It's funny how often statistics pops up where you least expect it. It's sort of running the background, isn't it? From like the ads you see scrolling online to how a bank figures out your credit score.
Oh, absolutely. It's this silent engine, as you said. Pretty much governs a lot of modern decision-making, whether we realize it or not.
So today, we figured we'd do a deep dive into, well, the basics, the real foundational stuff of business statistics. Our mission here is simple. Take all this sometimes dense source material, the terms, the ways data gets classified, the methods, and make it really click. Turn it into knowledge you can actually use to understand the business world around you.
Exactly. It's not just about number crunching in a vacuum. It's applying statistics, the science of it, specifically to make better business choices, which really means, managing risk better and spotting opportunities. And you see it everywhere: finance, operations, HR.
And definitely marketing and advertising, right?
Right.
That's probably where most of us feel it.
Yeah, very tangibly there.
Okay, so if we're going to unpack this, let's ground it. This isn't just theory. How are companies using these ideas right now? What are some really good examples from the sources?
Well, think about the snack aisle. The sources mentioned Kellogg's. Huge company, right? They run these massive research campaigns using statistical analysis just to figure out if people actually prefer Cheez-It over, say, Nabisco's Cheese Nips.
Mm-hmm. All that effort for crackers.
Millions of dollars riding on it. That whole decision is driven by stats from taste tests, purchase data, you name it.
Okay, I see. That's maybe lower stakes individually, but huge volume.
Yeah.
What about something with bigger price tags like TV ad rates?
Ah, good one. Advertising. The whole way TV networks price their ads, pure statistical inference. They set the rate for like a 30-second commercial based on data from Nielsen Media Research. And Nielsen gets that data by tracking, get this, about 41,000 specific households in the U.S.
Wait, only 41,000. And that determines potentially billions in ad revenue. Wow.
Yep. Really highlights how critical getting that sample right is. We'll definitely circle back to that.
For sure. And the big one everyone knows, or at least has heard of, the FICO score.
Oh, yeah. Fair Isaac Corporation. FICO. They use some pretty smart statistical methods to figure out how risky it is to lend someone money. So every time your bank sets an interest rate, they're leaning heavily on those predictive statistical models.
It's kind of everywhere then. FICO scores, even weather forecasting influencing energy companies. It's about turning numbers into, well, plans.
Exactly. Turning raw numbers into actionable plans.
Which brings us nicely to that first big distinction we need to nail down. Data versus information. So if I just have a list, say, high temp in Seattle was 19 last Monday, low was 7, that's just data, right? Raw facts.
Precisely. Data by itself, it's often just noise, doesn't really help you decide anything because it lacks context. Information. That's what you get when you process the data for a reason, for making a decision. So you take that raw temperature list, you analyze it over time, maybe find the average in New York City was, say, 3,827 consistently, and you conclude, okay, people without shelter are at serious risk of hypothermia. That conclusion, that's information. It pushes you towards an action, like opening emergency shelters.
Ah, I see. So data is the raw ingredient. Information is the finished meal, ready to be used.
That's a great way to put it. The transformation is key.
And just quickly on how we store this stuff, data sets versus databases.
Right. A data set is usually simpler, a collection of data points, maybe just one table, like temperatures for one city. A database, though, that's more complex, usually multiple tables, different kinds of data linked together. Think of that weather forecast database example. It doesn't just have temperature. It's got precipitation, snow, sunrise times, sunset times, lots of dimensions or fields you can analyze together. Much richer.
Got it. And briefly, where does data come from? Primary versus secondary.
Simple distinction. Primary data. You collected it yourself for your own purpose. Secondary data. Someone else collected it, and you're using it later.
And that difference matters, I assume.
Oh, definitely. If it's primary, you know its strengths and weaknesses intimately. If it's secondary, well, you've got to do your homework. Check the source, how they collected it, any potential biases. You have to be more careful.
Okay, makes sense. Let's shift gears. Before we can analyze anything, we need to know what kind of data we have. This seems crucial. The big first split is qualitative versus quantitative.
But that's the main fork in the road, yeah. Qualitative data is descriptive. It uses labels or categories. Think your name, your level of education, the brand of car you drive. You can count how many people fall into each category, sure, but you can't do math on the labels themselves. You can't add Ford and Toyota.
Right, no mathematical operations. So the other side is quantitative. Numbers.
Exactly. Quantitative data involves numerical values you get from either measuring something or counting something. Height, weight, number of customers, temperature.
But even there, it's not that simple. There's another split within quantitative.
Yes, and this one is really important because it dictates the kind of statistical tools you can use. We split quantitative data into discrete and continuous.
Okay, let's spend a moment here. This is often a point of confusion. Tell us about quantitative discrete.
Quantitative discrete data comes from counting. The question it answers is basically how many. It can only take on specific, separate values, usually whole numbers, because there are distinct gaps between them. Think number of students in a class, or goals in a soccer game.
You can't have half a student.
Exactly. You can't have 20.5 students or 2.7 goals. It jumps from one value to the next.
The source material had a neat example here that tripped me up at first. Shoe sizes. They use half sizes, like 7.58. Why are they still discrete?
Ah, that's a classic. It's a great point because even though they use half numbers 7.58, they are still distinct fixed steps. There's still a gap. You can't buy a size 7.2 shoe or 7.8. It jumps from 7.5 to 8. So because they are specific countable steps, they're discrete.
Okay, got it. Fixed countable steps, even if they include halves. So discrete is counting. What about continuous?
Continuous data comes from measuring. The question here is how much? This type of data can, theoretically, take on any value within a given range. The only limit is how precise your measuring tool is. Think height, weight, temperature, your exact salary down to the penny.
So my height isn't just 5'7". It could be 5.7 feet or 5.73 or 5.7345.
Yeah.
You can keep getting more precise.
Precisely. You can break it down into smaller and smaller units infinitely, in theory. That's the key difference from discrete data, which has those unfillable gaps.
And why does this discrete versus continuous distinction matter so much for the analysis?
Because the statistical methods are different. For discrete data, you might calculate the probability of exactly 3 errors occurring. For continuous data, like temperature, you'd be more interested in the probability of the temperature falling within a range, say, between 20 and 25 degrees. The math changes.
Okay, that clarifies things. So we've split data into qualitative, quantitative, then quantitative into discrete continuous. Now there's another layer, the 4 levels of measurement. Sounds like a hierarchy.
It is exactly that, a hierarchy of measurement scales. Each level builds on the one before it, adding more mathematical power as you go up. We start at the very bottom with nominal data. This is just about labels, categories. No inherent order. Think gender, blood type, car brands like we mentioned. All you can really do here is count how many fall into each category and frequency, and find the mode, which is just the most common category.
Okay, basic labels. What's the next step up?
Ordinal data. Now we introduce order, a ranking. Things can be put in a logical sequence. But, and this is key, the differences between the ranks aren't necessarily equal or meaningful. Think about movie ratings. 1 to 5 stars. 5 is better than 4, sure.
But the difference in quality between a 4-star and a 5-star movie isn't necessarily the same as between a 1-star and a 2-star.
Exactly. Or education levels, high school, bachelor's, master's. There's an order, but the distance isn't uniform. With ordinal data, you can find the median, the middle value when ranked, and the mode, but calculating a meaningful average is still out.
Right, okay, so nominal is just names, ordinal adds ranking. Now things get more mathematical, I imagine.
They do. Next up is interval data. Here, the intervals or distances between the values are equal and meaningful. Addition and subtraction now make sense. But the crucial limitation, there's no true 0 point. The 0 on the scale is arbitrary. It doesn't mean the absence of the thing being measured.
The classic example is temperature, right? Celsius or Fahrenheit.
Perfect example. 0 degrees Celsius doesn't mean there's no temperature. It's just the freezing point of water. 0 Fahrenheit is just another point, because 0 is arbitrary.
Ratios don't work. You can't say 40 degrees is twice as hot as 20 degrees.
We got it. Since there's no absolute starting point, multiplication and division, which rely on ratios, become meaningless.
And that's a big deal in business, isn't it, if you can't calculate ratios?
Huge deal. Think about it. No meaningful ratios means you can't calculate things like percentage growth accurately or return on investment, ROI. Those require division and a real 0 baseline. So interval data limits your financial analysis toolkit.
That makes total sense.
Yeah.
You lose that ability to talk about multiples or growth rates effectively, which leads us, finally, to the top level.
The top level, ratio data. This has everything the other levels have: categories, order, equal intervals, plus that all-important, true, 0 point. Here, 0 genuinely means the absence of the quantity. 0 height means no height. 0 sales means absolutely no sales. 0 weight, 0 age, 0 distance.
And because 0 means 0, all the math works. Addition, subtraction, multiplication, division, ratios.
Everything. All mathematical operations are meaningful and interpretable. You can say that $200,000 in sales is twice as much as $100,000.
So to nail that temperature point again, Celsius and Fahrenheit are interval.
But Kelvin temperature scale, that's ratio. Because 0 Kelvin, absolute zero, truly means the complete absence of molecular energy. That's the crucial difference.
Fascinating hierarchy. Okay, so now you know how to classify data and understand its mathematical properties. Let's talk about what statistics does. What are its main jobs? The sources mention 3 branches.
Right. Think of it as 3 main tasks statistics performs, often related to time: past, present interpretation, and future. They are descriptive, inferential, and predictive statistics. Descriptive statistics is the most fundamental. It's all about summarizing and organizing data that you already have, just describing it. The main question it answers is, what happened?
So this is like calculating the class average on a test, finding the mean median mode, making charts like histograms to see the distribution, basic reporting essentially.
Exactly. Summarizing the key features of your data set. No jumping to conclusions about a wider group, just describing what's in front of you. It sets the stage.
And then we use that description to do what? Make inferences.
Precisely. That brings us to inferential statistics. This is where we take that leap. We use data from a small group, a sample, to make educated guesses or draw conclusions about a much larger group, the population. The question here is, what can we reasonably conclude about the whole population based on the sample?
This is where things like election polling come in, right? Using maybe 1,000 voters to guess how the whole country might vote.
Perfect example. Or testing if the new drug is effective based on results from a small trial group. Hypothesis testing, confidence intervals. That's the world of inferential statistics.
Okay, so describe what happened, infer what it means for the bigger picture, and the third branch predicts the future.
You got it. Predictive statistics, or predictive analytics as it's often called now. This uses historical data, along with statistical algorithms and often machine learning techniques, to forecast future outcomes or behaviors. Its job is to answer what is likely to happen next.
And this is huge in business today, right?
Oh, massive. Forecasting which customers might leave, churn, predicting stock prices, using time series analysis, figuring out when a piece of equipment might fail based on its maintenance history. That's all predictive analytics.
So they really build on each other, describe the past data, infer if the patterns are significant for the whole group, and then use that understanding to predict what comes next.
That's a great way to summarize the flow. Describe, infer, predict.
Now, you mentioned something crucial for inferential and predictive statistics. The relationship between the population and the sample. You used the Nielsen example earlier. 41,000 households representing the whole U.S. Let's dig into that.
Absolutely fundamental. You can't really do inference or prediction without understanding this. The population is the entire group you're interested in studying. All registered U.S. voters, every single car produced by Toyota last year, all potential customers for a new product. We usually describe the population using characteristics called parameters. These are fixed values, but typically unknown because the population is too big to measure completely. We use Greek letters for them, like mu for the true population average, or sigma for the true population standard deviation. These are the numbers we want to know.
But we usually can't measure the whole population. It's too big, too expensive, maybe impossible.
Exactly. Imagine trying to poll every single voter in the U.S. Impractical. So what do? We take a sample. The sample is just a smaller, manageable subset selected from that population, like those 1,500 voters randomly called for a poll. We can measure the sample completely. The characteristics of the sample are called statistics. These are known values, but they can vary depending on which sample you happen to pick. We use regular Latin letters for these, like x bar x for the sample average, or S for the sample standard deviation.
Okay, so the whole game is using the known sample statistics, like X and S, to estimate the unknown population parameters, like Ningsuf.
That's the core idea of statistical inference, yes. Using the part we can see the sample to make intelligent statements about the whole, we can't see the population.
But everything hinges on that sample being a good representation, right? Otherwise, our estimates will be way off. Like that Nielsen example, if those 41,000 households weren't representative.
The ad rates would be completely wrong. Exactly. The quality of a sample is paramount. If your sample is biased, say, you only survey people in rich neighborhoods for an election poll, Your sample statistics will give you a terribly misleading picture of the overall population parameters. This concept of sampling bias is critical. Using proper methods, like a simple random sample where everyone has an equal chance of being picked, is crucial to getting statistics that accurately reflect the parameters. It's the bedrock of reliable inference and prediction.
Wow. Okay, we've covered a lot of ground. Let's recap quickly. We started with the difference between raw data and useful information.
Yeah, data needs context and analysis to become information for decisions.
Then we learned how to classify data, qualitative versus quantitative, and the key split within quantitative, discrete counting versus continuous measuring.
And how that dictates the math you can do.
We climbed that hierarchy of measurement scales. Nominal, ordinal, interval, where ratios break, and finally, ratio, with its true zero allowing all math.
Understanding which level your data is at tells you what analyses are valid, especially important for things like ROI.
And then the three big jobs of statistics. Descriptive, what happened. Inferential, what can we conclude about the population. And predictive, what will happen next.
Describe, infer, predict, using samples to understand populations.
Which brings us back to that core challenge. We know that inferential and predictive statistics rely almost entirely on using a relatively small known sample to make claims about a vast unknown population.
That's the essence of it.
So thinking at everything we discussed, from FICO scores affecting your finances to ad rates to maybe even weather forecasts, if it all hinges on that sample. What stands out to you as the single most critical factor, maybe even the riskiest assumption, in making sure those predictions are actually accurate?
A final thought. Well, given everything relies on that leap from sample to population, I'd say ensuring that sample is truly representative, minimizing that hidden bias that feels like the linchpin. All the complex math that follows is useless if the starting sample doesn't accurately mirror the population you care about. Getting that foundation right, that's everything. What do you think?